Seashells arrive at this factory by the ton, and the first thing engineers care about isn't beauty, it's contamination, moisture, and particle control. Raw shells come from seafood processors, aquaculture farms, and coastal collection programs. And they're loaded with salt, sand, organic tissue, and bacteria that will permanently stain a tabletop if the plant doesn't neutralize it fast. The intake line starts like a mineral plant, not a craft shop. Loads are weighed, lot-coded, and sampled for grit content and organics, because sand destroys cutting tools and residual protein causes odor and yellowing under resin. Conveyor hoppers feed shells into a trommel screen that separates oversized debris from fines, and magnets and metal detectors protect downstream crushers and pumps from hooks, staples, and wire. Washing is staged and aggressive because shells are porous. High-pressure spray tunnels knock off surface slime. Then, rotating drum washers tumble shells against each other to shear away remaining tissue. Many plants run countercurrent water to reduce consumption. And they capture solids in settling tanks because shell wash water carries heavy grit that will wear pumps if it's recirculated unfiltered. The next critical step is deproteinization, because any remaining organic matter becomes a future defect. Depending on product grade, the factory uses hot water cooking, alkaline baths, or controlled steam treatment to loosen proteins and sterilize the material. Temperature and time are tightly controlled. Too mild and proteins remain. Too harsh and shells become chalky and brittle, losing the sharp, iridescent surfaces that make luxury inlay look expensive. After thermal treatment, shells are rinsed and often bleached. But bleaching here is engineered color correction, not just whitening. Hydrogen peroxide systems are common because they oxidize stains, without leaving chlorine residues that can react with resins later. For factories producing mixed-color mosaics, bleaching may be reduced or skipped to preserve natural reds, creams, and blues. And instead, the plant focuses on sanitization and odor removal. Drying is where a lot of shell table factories quietly win or lose quality. Shells hold moisture in microcavities, and moisture trapped under resin causes bubbles, clouding, and delamination. So the plant runs belt dryers or batch ovens with controlled airflow until moisture hits a narrow target. Inline moisture checks prevent over-drying that turns shells dusty and fragile, and prevent under-drying that becomes a defect weeks later when the table warms under sunlight. Now the line splits into two main product streams: shell chips for terrazzo-style surfaces, and shell tiles for mother-of-pearl style inlay. For chips, the dried shells go through crushing and grating. A jaw crusher breaks shells into fragments, then roll crushers and hammer mills refine size. Screen decks separate chips by millimeter range because the visual texture of the tabletop depends on chip distribution. Fine dust is removed by air classification, since dust increases resin demand and makes the surface look muddy instead of crisp. Dust control is a safety and quality system at the same time. Shell dust is largely calcium carbonate. Airborne particles are a lung hazard and a contamination risk for resin coating. High-tech plants run negative pressure hoods, cyclones, and baghouse filters. And they monitor differential pressure to know when filters are loading up. Good dust control also prevents microparticles from landing on wet resin surfaces, where they create tiny pimples that ruin a glossy finish. For inlay-grade shell, the process becomes much more precise. Shells are cut into workable blanks, then flattened. Water-cooled saws slice sections to minimize heat and cracking. Because shell is a layered composite, and heat can cause microfractures that later show as white lines under polish. The flattened pieces go through thickness, sanding on wide belt sanders with calibrated pressure, producing tiles with consistent thickness, so they sit perfectly level in the table. Surface. Sorting is where this becomes high-tech. Camera systems and optical sorters classify pieces by color, luster, and defect patterns. Iridescence isn't just a look. It's angle-dependent light interference. So premium factories use controlled lighting angles and multiple cameras to predict how pieces will read under indoor and outdoor lighting, pieces with dull nacre, excessive pores, or dark inclusions are diverted to lower grade products or crushed into chips before shells ever touch a tabletop. The factory must decide what the tabletop actually is. Solid wood, engineered wood, stone, metal, or a composite panel. High-volume production usually uses engineered substrates, MDF, plywood, or cement board because they're flat, stable, and predictable under humidity. Substrates are cut on CNC routers, with tool paths designed for consistent pocket depths if the shells will be inlaid, or perfectly flat surfaces if shells will be cast into resin. If the product is a terrazzo-style seashell table, the shell chips are blended like an engineered aggregate. The plant measures chip size distributions, then mixes them with pigments and optional fillers to hit a repeatable look. Some factories add recycled glass or stone chips, but shells are the feature, so they control chip percentage carefully. Too low, and it looks like ordinary terrazzo. Too high in resin can't fully wet the mix, causing voids and weak spots. Resin selection is a major engineering decision because it controls durability, UV resistance, yellowing, and heat tolerance. Epoxy delivers clarity and strong bonding, but can yellow if UV inhibitors aren't used. Polyester resins cure faster and can be cheaper, but odor and shrinkage control become bigger issues. High-end plants increasingly use UV-stable systems or top-coat layers. It's designed specifically to resist sunlight and cleaning chemicals. Mixing resin is never pour and stir at factory scale. Metering pumps deliver resin and hardener at precise ratios, and high-shear mixers blend without trapping air. Vacuum degassing pulls bubbles out before casting because bubbles are the enemy of a glass-clear tabletop. The plant monitors resin temperature because viscosity changes with temperature. Thicker resin traps bubbles and weights chips poorly, while overly warm resin cures too fast and can crack from exotherm heat. For cast surfaces, the factory uses molds or perimeter frames to define thickness. The shell resin mix is poured onto the substrate, then leveled with screed bars. Vibration tables shake the assembly to settle chips and release trapped air similar to concrete consolidation. The vibration frequency is tuned. Too much vibration sinks chips and causes separation. Too little leaves voids and weak bonding for inlay tables. The process is closer to precision woodworking and jewelry making. CNC routers cut thousands of small pockets or geometric channels based on a digital design, and pocket depth is controlled within fractions of a millimeter, so shell tiles sit flush. Adhesive is applied in controlled film thickness. Then shell pieces are placed sometimes by trained workers, sometimes by pick-and-place robotics for repeating patterns. Alignment matters because the human eye detects crooked grids instantly. Luxury buyers pay for symmetry. Once shells are placed, the gaps are filled. This can be clear resin for a floating look, tinted resin for contrast, or a fine mineral grout. The fill material must bond to both shell and substrate, resist shrinking, and sand evenly. Shrinkage control is critical. If the fill sinks after curing, you get low spots that catch dirt and look cheap. Curing is treated like a controlled chemical reaction. Thick resin pores generate heat, and uncontrolled heat can warp substrates, create microcracks, or cause yellowing. High-tech plants cure in temperature-controlled rooms and may use staged cures. A slower initial cure to reduce exotherm, followed by post-curing to maximize hardness. UV curing may be used for thin top coats because UV systems can lock a surface quickly, reducing dust contamination and increasing throughput. After cure, the table is not finished. It's rough and uneven by microns 2 millimeters. Flattening is done by wide belt sanding or CNC surfacing heads that plane the cured surface to perfect flatness. This step is where shell tables become expensive to manufacture, because shells are hard and abrasive, and they destroy sanding belts and cutters. Tooling schedules and dust extraction are engineered to handle calcium, carbonate abrasion, and keep the line running. Then comes multi-stage polishing, which creates the wet look gloss people associate with luxury. Polishing moves from coarse abrasives to fine compounds, and each step removes the scratch pattern from the previous one. Factories often use automated polishing heads with controlled downforce. because uneven pressure creates swirl marks and dull patches. Water-fed polishing reduces heat and keeps dust down. But water management must be perfect because water trapped in micropores can haze the finish under certain resins. Edge finishing is a separate process because edges are impact zones. CNC edge profilers shape bevels or radiuses. Then edge sealers protect against chipping and moisture intrusion. If the table has a wooden core, the plant applies barrier coats so moisture can't migrate into the substrate and cause swelling that cracks the resin skin. Protective. Top coats are applied to improve scratch resistance and chemical resistance. Some plants use hard clear coats similar to automotive coatings, applied by spray robots to keep film thickness uniform. Others use specialty resin top layers with UV absorbers to reduce yellowing. The top coat choice is tested against real-world threats: alcohol wipes, acidic drinks, heat from mugs, and abrasion from daily cleaning. Quality control is continuous because the defect modes are predictable. The factory checks for voids with visual inspection under angled light because voids show as tiny black pinholes. Gloss meters quantify surface reflectivity because looks shiny is subjective, but gloss units are measurable. Flatness is checked because a table that rocks on a flat floor is an immediate reject. Adhesion is tested with crosshatch or pull tests on sample panels to ensure and substrate bonding won't fail after months of temperature. Cycling dot color consistency is another high-end requirement. Shell is natural and varies, so the factory manages it like wood grain selection. They batch shells by tone, they build recipes for chip blends, and they map surface layouts before final bonding. For premium orders, pieces are matched in the same way stone slabs are book matched, because visual harmony is the product. The base and frame assembly happens in parallel. Metal bases are welded and powder coated, wood bases are machined and finished. And mounting points are designed to allow movement. This matters because resin would expand differently with temperature. If the mounting is rigid, stress transfers into the tabletop and causes cracks. High-quality factories design floating mounts, and use elastomeric adhesives or gaskets that absorb differential movement. Packaging is engineered because polished resin surfaces scratch easily. Tables are wrapped with protective films, foam corner guards, and rigid crates that prevent vibration rubbing during shipping. Even the stacking orientation matters, because a heavy tabletop flexing during transport can stress the resin shell composite and create hairline cracks that only show under certain light. Waste handling is part of what makes the facility modern. Shell residues and fines can be routed into calcium carbonate filler streams for other industries, but only if they're kept clean and separated. Resin waste is minimized with accurate metering and batch sizing. Wash water is filtered for grit and solids, because shell processing produces heavy sediments that must be removed before discharge. What makes this Seashell factory high-tech is that it treats a natural variable material like an engineered input. Shells are cleaned to food-grade levels to prevent odor and staining. Moisture is controlled to protect resin clarity. Chips are graded to control visual texture. Resin chemistry is metered and degassed like a composite plant. CNC machining controls inlay geometry, and polishing turns a rough cast surface into a mirror finish. The final table isn't just shells glued to wood. It's a precision composite surface built from waste material, manufactured with the same process discipline you'd expect in automotive coatings and engineered stone, because that's the only way a raw seashell becomes a flat, glossy, durable tabletop that looks expensive for years